Hey everyone, my name is Kristian. I'm a senior staff software engineer at Flock Safety. My first droidcon. It's pretty cool to meet a whole bunch of people here, and please meet with me after this because I've enjoyed discussing a lot of the people here. I'm going to talk today about deploying Android AOSP at scale. Here is the overview though. First we start off with what is the scale of this deployment? How has Flock customized hardware? What versions of AOSP are we using? Building apps and OS for deployment. How do we actually deploy these things? Monitoring them once they're deployed. How do we configure them in the field? Debugging them. And any self-recovery techniques. So we have 71,000 devices deployed out in the field across the 45 states. We capture up to 6 billion images per day, and up to 500 million of these are uploaded to the cloud. So as you can see already, it's okay, you capture 6 billion, you upload 500 million. There's a bit of edge processing going on here, right? So yes, we use AOSP with Kotlin services on the device to do this processing. The products themselves, you can see the top one just out the door. We've got an example of that. They're AOSP-based cameras that use LTE, Wi-Fi, and Bluetooth for connectivity. They are solar powered, so if you can dig a hole in the ground and put up a 12-foot pole, you can put one of these and a solar panel on the top, and you are good to go. As you can see, there is no display on these, which is a bit different to the other discussions and presentations we've seen around here. It is a headless device. And it really operates in all climates. We're talking to below freezing to Death Valley type temperatures. We also have custom hardware that we use in these. Apart from the internal storage, which is normally like an eMMC or UFS storage, we have SD cards, NVMe drives, and hard disk drives to store all the evidence that is captured on these devices. We have the internal and external batteries. We use this custom hardware for cold temperature mitigation. So if you're using a lithium-ion battery, below freezing, it stops actively charging. Below minus 20 degrees Celsius, it actively discharges all by itself. So this custom hardware actually detects these low temperatures, warms itself up, so it can continue to supply power to the camera. We've had a few years to try and a few iterations of this to get right. It's a very difficult thing to get right. Putting any device out in the climate, in the harsh climates like this, it's amazing how some of them are operating after this time. We have multiple different types of camera sensors across our devices, supported by an excellent internal imaging camera imaging team over in Finland. They do the camera tuning and driver development. You can see to the right one of the setups that they typically use to do this tuning. We have an IR LED sync with the camera shutter. This is a custom change to the Android stack. Basically, when the infrared LEDs go off, which is typically at a nighttime scenario, we're flashing the LEDs to illuminate plates of cars going by. We sync the camera shutter with that. We don't want to have the infrared LEDs on the whole time. That's just wasting power, just throwing photons out that we're not going to be using. So we turn the infrared LEDs on just before we open the camera shutter, close the camera shutter, and then turn off the infrared LEDs. This is for power savings. Remember, we are a solar-powered device. We want to conserve as much power as possible at night. And then we do a frame capture after a motion trigger. So while the camera stack is mostly active, we are waiting for a motion event before we start streaming images through. And we don't want to be processing images that we know we're not going to be using. So again, this leads to more power savings. We also have this hardware being custom. We have an in-house hardware design team, distribution teams and factories. The example here on your right, you can see is one of the tables where we're actually assembling the devices in the factory. And we pretty much account for all parts of the product lifecycle. Refurbishment, taking devices that have failed back in, doing whatever needs to be done, fixing the lenses, whatever the case, and putting them back out to work in the field. We have software support for this custom hardware. We try to reduce changes to AOSP itself as much as possible though, so we're using overlays, XML configs to achieve this. We write custom services that are living independently of the Android code that's running. And we found that this eases upstream code integration. Basically, when we get a code drop from Qualcomm or other partner, if we've made changes to the same files that they have in the framework, then that's going to cause a lot of merge conflicts that we have to work through. Done that before, don't want to do that again. So we try and keep our changes as far away from that as possible. The storage is bolted onto the side, so the NVMe drives that I spoke about, for example, They are mounted in FSAB files, and we separately encrypt them with LUX encryption, for example. And we do this because the evidence that we capture, if we have to like factory reset a device, we want to keep that evidence, right? We might want to clean up the issue that was causing the original error with the Android stack, but a factory reset is normally a good way to do that. But we want to keep the storage on the external, keep the evidence in the external storage device and maintain its integrity. And we have a peripheral service that abstracts these different hardware differences. So on all the different products we have, we might have a status LED that we want to turn green. So we have a peripheral service, it's a Kotlin service that's saying, okay, which product am I on? Am I on product A, B, or C? And we have sysfs files generally exposed to say, hey, these are the GPIOs that we're using for these different LEDs. They're going to differ per chipset, right? And so the peripheral service is going to go, okay, I'm on product C. These are the sysfs files that I'm going to be using to set the status LED green. So cool, let me go do that. And this provides like, the other applications are going to be using this peripheral service to talk to hardware. They're just calling this interface set status LED green. They don't need to worry about anything else. The Android variants that we support range from Android 8.1 up to Android 13. Show of hands, who here has actually built AOSP from scratch? Okay, so we've got like 4 people, a couple of Flock engineers as well should be there. So yep, built AOSP, that's great. We have Kotlin-based headless Android services that are running on the device as well, around 20 of them. We don't have a Play Store. We have a custom updater that is included in the OS image that reaches out, and we have our own custom deployment schemes that I'm going to get into about like, how do we do this deployment. And we're a Qualcomm partner as well, so we enjoy the same level of support as any other phone manufacturer would. So talking about the Kotlin microservices architecture, we have, like I said, around 20 services. You can imagine the top lane here is the car going by. That's our media pipeline applications. We don't want to disturb them when we're doing updates. The bottom ones are services. Maybe it's doing debugging services or just general integrity services. So evidence is going to go through. Cool. We're going to send some updates in. Evidence is still going to go through. Cool. Not be affected by the updates. Even more updates. Cool. Still getting evidence through the system. So this is why we use the microservices architecture, so we can, plug and play and try and, not affect the media pipeline as much as possible. And indeed, if one of these services happens to be having an issue and crashing, it's not going to be bringing down our whole evidence capture system. We used to be a polyrepo. Historically, each application had its own repository. We moved away from this into a monorepo. It was very difficult to keep repos in sync with their dependencies. One app might have a dependency on version 1.0 of a Gradle library, another one on 1.1, and it was a mix and match, and it was very chaotic to try and get those all in sync. Shared libraries between apps became difficult to maintain. If we had any dependencies that were generated, they would get uploaded to Artifactory, and you're in the next repository over, so okay, now I have to either deploy that locally to that other application or download it from Artifactory. And of course, like I said, Artifactory is required when sharing these libraries. We've mainly been able to do away with the need for Artifactory by moving into a monorepo. And it's simple to make changes across multiple applications. We can do a single PR in GitHub across all the applications, makes it really nice and easy. Dependency publishing is much easier. We assign code ownership via paths in that repository. We found an easy way to do that. It's easy to specify that single version of a dependency, so I'm using this Timber log wrapper or something. I can specify 1.0.1, whatever it is, and every application is going to be using that dependency. And then all the APKs that we use, like the 20 or so, are generated from this one monorepo build. How do we do this building? We use Jenkins extensively for OS and applications. The apps code is located in GitHub. Android OS code is located in Gerrit. We have a common apps build pipeline, so we go off, build the apps. We get all the apps for the different products that we have. But we have a unique OS build pipeline right now. This is painful. So we have, if you consider an AOSP source tree as a polyrepo, we have 3 of them, so we have polyrepos. I'm starting to sound like a parrot. This is very painful, and if I have to build a separate OS for each of them, it takes a lot of time, and you're looking at, for Android 13, we currently have 1,800 repositories that we have to deal with for that product, with the vendor and product partitions. So we are looking to sort of do a lineage OS style model where we actually have one single manifest, and from that we have launch targets for all of our products. So we're looking forward to that, in deploying that in the near future. Here at Jenkins Pipeline, we can create builds for any pull requests that we have. We can create releases for user debug, and what we call no IP builds. These are builds that we might send to the FCC for compliance testing. They're just pretty much builds is very close to vanilla AOSP. It doesn't have our applications running on it. And then we can create the Delta over-the-air updates for OS builds. Instead of sending a 700 megabyte OS build out to the ether, we instead can reduce it to like 50 megabytes. We don't want to deploy 20 applications separately. That would be harrowing. So we use a manifest to say, hey, 1.0 includes these versions of apps, and we deploy them all together. If no changes are made to an app, it still refers to the previous version, but in apps A and D here, they got 1.1, so we call that manifest version 1.1. C was upgraded to 1.2, so we call that manifest version 1.2, and then so on and so forth. When we deploy the devices, early days we used to use SQL to do the deployment. Today we use a custom deployment interface to not worry about the SQL queries and like, did I get this right? So here you can see like this is for the OS over-the-air update. We have versions 2.71 and 2.61. We have build information, and you can see these little colors here, like the yellow pill, the green pill, and the red pill. The yellow pill says this is deployed to a cohort of devices. The green says this is the current global version, and the red means this is deployed to an individual device. The devices in the field ask what version of code should I be on, and the replies from our servers are saying you should be on this version, and this is the URL to go download it from. Deployment from our builds goes to auto test rigs. This is a typical auto test rig we have for some initial testing to make sure that the device boots, does it have basic services running. And then we can start deploying the cohorts out in the field, which you can see like the cohort 8 is pretty big. It's nearly 15,000 devices. Cohort 1's tiny, around 80 devices. Each cohort, even the cohort 1, is representative of the fleet as a whole. So we try to cover all the LTE types we support, like Verizon, FirstNet, AT&T, all those are in that cohort, plus the different types of camera modules, plus the locations. Are they up north, are they down south in the colder or winter or warmer climates? And we typically do this deployment as one cohort per day, and then we go to monitoring them. Every 20 minutes, the devices are pumping out a status message saying, this is what I've done, the battery, RAM, disk usage, how many images I've captured, a lot of other dimensions about the data. And then we can feed this info into Grafana to roll some pretty cool charts. So this is one of the rollout charts we might typically look at. The green slice there is the new OS version that's rolling out, so you can see it's got a little piece of the pie. And over the day, we can see that increase as our rollout is continuing. This is like a week of data. We can see exactly what versions. We can drill down to a particular device to see if it's having any issues. And we can see over time what versions have been on that device. And then we can correlate that with CPU temperatures, CPU loads, modem signal strength, the modem CID, what tower it's landed on. Any of these dimensions, we have so many we report, and we can see, is there a particular OS or apps version that is affecting the performance of the device in any way? And it's really simple to correlate that with this in the Grafana. You're just looking down and going, oh yeah, cool, I can see that this is affected, or we're now reporting the RSSI for a modem value much better. We can configure the devices. We use JSON to configure devices in a slot. A slot is a position, a physical location in the field. And we use that to say if we need to replace a device, that new device will just inherit that slot's configuration. We have 250 settings. Here's an example for what we might use for a power consumption setup in the lab. But we can also use these as feature flags. So we want to roll out a new feature. It's there in the code, it's dormant, but through these configuration options, we can go and activate it. We've grouped these into pre-configured things, like so the support mode, for example. Typically the device is phone home every 20 minutes. We can say, hey, support mode, for the next 28 minutes, phone home every minute, because I want to monitor exactly what you're doing. We can also, this other toggle here is the low power mode, so instead of taking images at 5 frames per second, take it at 1 frame per second to conserve as much power as possible. We can also send device commands like a reboot, factory reset, go and provision yourself for Auth0 if you haven't, generate crash packs. This is the thing we use for debug information. And then talking about debug information, we send crash information to Datadog. We use bug reports extensively in our crash packs. Bug reports, I love Battery Historian. I know it's been deprecated, but I do love being able to grab this pack from a remote device and get graphs like this to tell me exactly what the device is doing in high detail. We can run it through other tools like Check Bug Report, which is a Sony tool. Persistent logcat logs we have, so we can get previous reboot cycle information from the device as well. And then when things go wrong, when you lose connectivity on your Android device, what are you normally doing? Restart the device, you might toggle airplane mode, something like that, right? How about when the user data partition's full? Do you go to Google Photos and say, delete all the photos I've uploaded? That's what I do. Or I'll go and get rid of the podcasts that I've downloaded, some of them at least, so many. How about low battery? You go plug it in, right? We can't do that. This is where the device is out in the field. So we have to have autonomous services that look at this information and decide, well, okay, I've got lots of connectivity. I'm going to try and reboot. If that doesn't work, it reverts the settings, those configuration options to the default for that device. Maybe we sent out a bad configuration setting. If that doesn't work again, we revert the apps to a previous version. We can also hibernate when the battery is getting too low. The device can say, hey, I'm below 10% battery level. I'm going to go to sleep for a while. Hopefully I've gotten enough solar charge in that period. And when I wake up again, it's like, cool, I can get back into action. We also do periodic media cleanups to maintain disk space, clean up logs if the user data partition's too full. And we have watchdogs. If any processes get stuck and are not pegging the watchdog will bite and reboot the device. Sometimes, as much as we try, there are some things we cannot fix remotely. So I've got a few images here to show what that might look like. Like I said, our devices are out in the field. I could nearly imagine we could be trying to sort of melt the snow off of this device by turning the infrared LEDs on. But you know, there's another problem. There's snow on the solar panel, so it's probably not got enough power to do that anyway. Some people are terrible drivers. We see this quite happens more often than you want. A lithium-ion battery does not react well to bullets, and they tend to catch on fire. And a camera device does not work that well when it has been spray painted. We see lots of types of these things out in the field. But this wraps up my discussion. Thank you so much for attending.